So welcome to lesson 4 in our study of mathematical biology 2. So in this video we'll talk about non-dimensionalization. Okay. So non-dimensionalization is the full or partial removal of physical dimensions from an equation involving physical quantities by a suitable substitution of variables. And non-dimensionalization does the following. So it fully or partially removes the units, it scales down the variable to proper fractions, and it reduces the number of parameters in an equation for analysis. So for instance, you might have an equation with several variables, okay, and you would want to reduce the number of variables for easy analysis. You can apply a concept we call the non-dimensionalization. And mostly in mathematical biology, that is what we do. We non-dimensionalize equations or models to reduce the number of parameters in it to make analysis very simple. Okay, but unfortunately there is no particular or systematic procedure for non-dimensionalizing equations, so it doesn't have a straight method that do this or do that. All right, but in this video we are going to illustrate how to do it, and we are going to use the Verhoeven's logistic model in 1938, and we will use the Ludwig's model on Bedouin to also do that. Okay, so let's just take the Verhoeven's logistic model in 1838. So this was the Verhoeven's logistic model. So you can see that it has two parameters here, R and K. So if you want to non-dimensionalize this, that means you want to reduce the number of parameters, right? So when we are starting, one approach that we can use is that we are going to create new variables to represent the old variables. Okay, so we will create a new dependent variable, and that new dependent variable should be expressed in terms of the old one. So here, for instance, we know that from this question we have two variables. P is the dependent variable and T is the independent variable. So I want to create a new dependent variable called v. So I have to make sure I express the v in terms of p. So I say let v be equal to p over k. That means p will be equal to v times k. That's well understood, right? Then I also want to create a new independent variable called tau, and I have to also express that one in terms of the old one, which was called t. So I say let tau equals t. So when I have this, that means that now I'm going to change everything from the p, the t to the v, the tau. And to be able to do that, I have to use the chain rule to be able to derive that. So using the chain rule, I can write the p, the t will be equal to the p, the v, that's the new variable we are introducing, times the v, the tau, then times the tau, the t. So you can see that when you look at the right hand side, the same as the p, the t. Okay, so we have p to be equal to v times k and tau to be equal to t. So that means we can find the p, the v, and the p, the v will be equal to k, all right, from here. And the t, the tau will be the tau, the t will be equal to 1. So that means we can make substitution here. And when you make substitution here, we will get the p, the t will be equal to k, the v, the tau. So now we can make substitution into the main logistic equation. Wherever you find the p, the t, we put k, the v, the tau. Wherever you find p, we put v times k there. Okay, so this is what will happen when we make substitution. So now the p, the t will be equal to k times the v, the tau, which will be equal to r. And wherever you find p, we put v times k. Then 1 minus p over k. But we said p over k is the same as v, right? So you can see that the k will cancel the k. and we get the v in the tau will be equal to r times v, or multiply 1 minus v. And one thing about non-dimensionalization is that when we non-dimensionalize an equation, we don't want to see any of the old variables in it. So you can see the old variables and the old parameters. We don't want to see any of them in it. So you can see the old variables were p and t. We can't find them here because now we have new ones, v and tau. But the old parameters were k and r. The k has been eliminated, but we still have r. So we have to make sure we don't have the r then. So we can say let a certain alpha be equal to r, and now we have the v in the tau will be equal to alpha times v minus 1 times v. So you can see that we have non-dimensionalized the logistic growth model. It was having two parameters originally, but I reduced it to just one. That is alpha, right? So we had just one parameter because of the approach we used. So we can also use a different approach. I told you that when it comes to non-dimensionalization, we don't have any systematic procedure for doing that. Okay, so it's like a try and error something. So there's a non-dimensionalized equation for the logistic model, and here we have reduced the number of parameters from 2 to 1. So as I said, we're going to use a second approach, which is going to take away all the parameters from it. Okay, so we will have our logistic growth model here, and we say let v be equal to p over k. So we always define the new dependent variable in terms of the old one. We also define the new independent variable in terms of the old one. So tau, which is the new independent variable, is equal to r times t. Like I told you, there is no systematic way. It's a try and error something, okay? But actually, doing this should give you some procedure you can follow in doing yours, even though it's not systematic. So now we are letting this be our vein, this be our tau. So that means p will be equal to k times v, right? Like using a chain rule, the p dt will be equal to the p the vein times the v the tau times the tau the t. So from here, the p the v will be equal to k, and from here, the tau the t will be equal to r. So we make substitution. You have k here, you have r here. So that means the p dt will be equal to k times r the v the tau. So we take this and we make substitution into the main equation, right? So doing that is going to give us k r the v the tau will be equal to r k v times 1 minus v. And you can see that kr cancels kr, and I'll be left with the v the tau will be equal to v times 1 minus v. So you can see here we have reduced the parameter from 2 to what? 0, and we have non-dimensionalized the logistic growth model. Okay, I hope you understand. Okay, so let us take one last example on the Ludwig's model on bedworm. So this is the Ludwig's model on bedworm. It was given by what we can see here. Okay, and this here is what we call the Hoiling effect. So we have four parameters R, K, A, and B, and we would want to reduce the number of parameters. So we let V be equal to P over A. So that means that P is equal to V times A. And we let tau to be equal to RT. Like I told you, there is no systematic way of doing it. It's a try and error something. Okay, so you can let V be equal to anything, but always make sure you define the new dependent variable in terms of the old one, and you also define the new independent variable in terms of the old one. And the rest is you try to work around it to eliminate the constants, some of them, the parameters, sorry. So using chain rule, we have the p d2 be equals to the p the v times the v the tau times the tau the t. So we have p is equal to v times a, so that means the p the vein will be equal to A, and the tau dt will be equal to R. So when we make substitution here, we will have the PD2 be equal to AR the vein the tau. So now we come here and we take this and we put it inside this. So wherever we find the PDT, we'll write this. Wherever we find P, we write vein times A. So doing that, we'll get AR the vein the tau will be equal to AR vein 1 minus AV over K minus B A squared vein squared over A squared plus A squared vein squared, right? So when it comes here, we can factorize A squared out from both the numerator and the denominator. So when you do that, we are going to get this. And they can cancel out to give us what we have here. So you can see that we have AR here, AR here, and we also want to get a certain AR here so that we can eliminate the ARs, okay, those two parameters. So we can say the B here, let it be equal to R times A over alpha. So doing that is going to give us, when we make the substitution, we'll get R times A over alpha. Wherever you find the B, we put R over A over alpha there. And doing that means we can write this here in terms of this, right? We can bring the AR out. So now our ARs can cancel through, and we'll get the V in the tau will be equal to V times 1 minus AV over K minus V squared over alpha 1 plus V squared, right? But you can see that we still have some old parameters here, that is A and K. So you can say let gamma be equal to A on K. And when you do that, we will get the V in the tau will be equal to V 1 minus alpha v, then minus v squared over alpha plus 1 over v squared. Okay, so you can see that we have non-dimensionalized the Ludwig's equation that we had for bedworm, and it had 4 parameters, and now we have just 2 parameters, gamma and alpha. Okay, so this is the scaled equation, and this is the non-dimensionalized equation. So when it comes to non-dimensionalization in mathematical biology that we are doing, we are mostly interested in reducing the number of parameters in that equation to make analysis very simple. Okay, as I said, there is no general way of doing it, but at least there are some key things that you have to know. That you have to always express a new independent variable in terms of the old, the new dependent also in terms of the old, and you have to make sure that after your non-dimensionalizing, you shouldn't have any of the old parameters in the equation and any of the old variables as well. Okay, so thank you very much, and see you in the next lesson.